Yeah, all right, let me send the other link right now. All right. Yeah, all right, let me send the other link right now. Okay, so screen. Right.
Checking how these.
This good?
Yeah, it's working.
Okay. Hello.
Yeah, random pizza. Jing-Chen. Sorry.
Yeah, that's mine. Me. Hello, what's up? Can you check whether like this window is being shared in the live stream?
It is live stream.
Hi, what's up?
It is live stream, but I'm not sure.
Yeah, can you check it right now? Because I want to make sure that, or you can enter my Zoom. Hi, what's up?
Yeah.
Are you for the journal club? It's showing? Okay, cool. Nice. Yeah, try to sit yourself and get some pizza. Probably.
I just got out of. I'm supposed to be in there too, but yeah, I'm skipping it.
Yeah. Anyone wants to introduce me? Yeah.
This is Kim Woo. This is Emily. They're both from my year, but
Okay. Yeah. So are you
I forgot about
experimentalist or
I'm a nuclear theorist.
nuclear theorist? What about you?
Particle experiment.
Oh, okay. Okay. So we have a like very hybrid background. Yushan, do you want to introduce me like to the audience online right now? Yeah.
This is Jing-Chen. He does a lot of analytical stuff. And here today is going to give an introduction to Chern Simons theory, perhaps more to the experimental side. Take a look.
Yeah. Thank you, Yushan. Hello, everyone. So I am Jing-Chen, and I'm right now a PhD student with Professor Mohammed Hafezi. I was doing some research in open quantum systems. So today I want to talk about some Chern Simons theory. And this talk is targeted into both theorists and experimentalists. By saying experimentalists, I mean just the Chern Simons theory is not like expertise in your field. So I would like to deliver the talk about like the simple derivation of Chern Simons theory by using like a linear response theory. And also I will show some very fascinating properties about Chern Simons term. And I will show naively the ground state degeneracy of the fractional quantum Hall states with a simple derivation from the Chern Simons theory. And for experts and theorists, I want to convey that Chern Simons theory is a topological quantum field theory, by which I mean that its properties does not depend on the unit or the scale of your field, but on the topology of your global system only. And I will show the heuristic RG flow from Priskin's model on integer quantum Hall effect, by which you can see that the RG flow of the conductivity will flow to some fixed point, and that kind of explains why Chern Simons theory is topological or is a TQFT. Also, by analyzing the property of the Chern Simons term, I will like give you like a flavor to appreciate on why it is called like topological phase transition when we're discussing Chern Simons terms. In the end, I will give some examples on how to use Chern Simons term to find more systems in order to explain them. I will give the Hall viscosity as an example. So it's a very technical example, but I think once you get the flavor, you can probably apply that into some more mathematical applications, such as lattice disinclination or lattice dislocation, which can both be explained by Chern Simons term. All right, so this is the outline of today's talk. I'll give the experimental motivations, and then I'll give some derivations from linear response. Then I'll talk about the Lagrangian Hamiltonian approach. Finally, I'll talk about some TQFT properties of Chern Simons theory. So let's review like two important experimental results. So the first one is the experimental data from the fractional quantum Hall, right? So on the right-hand side is the famous paper, famous PRL paper that wins them the Nobel Prize. So this is the figure of the Hall resistivity versus magnetic field. So the curve above has a lot of plateaus which are integers, and those are the integer quantum Hall effect. So you can see some plateaus of 4, 3, 2, 1, etc., etc. However, for the same system, if you are increasing the magnetic field such that you have very strong Coulomb interaction and you have like a low enough temperature, then you can observe some of the Hall resistivities with some fractions. For example, you can see the famous fractions of 3/2 or 1/2, etc. And this is very precise. I can say that in the past 20 or 30 years, a lot of groups have reproduced their results, and they found amazingly that the Hall resistivity, they remain a constant apart from the linear growth part. Like once it reaches a plateau, you can always like see some constant and fixed Hall resistivity. For most of you, I assume that you have learned more or less about some Barry phases or the AB effects in the quantum mechanics course. So that you, I assume that you're familiar with the definition of the Barry phase, which is defined by the divergence or of the block function in the Brillouin zone. Sorry, this is the Barry connection, and the Barry phase is the integral of the Barry connection around the whole Brillouin zone. And you may have heard a lot of talks talking about the topological insulators or quantum Hall effect. That okay, the reason why integer quantum Hall effect has like integer numbers of like e squared over h is because that if we integrate over the Barry connection over the whole Brillouin zone, you get an integer, right? So that's very familiar to lots of the our young audience, especially in the topological era. However, it is a little bit hard to apply that kind of logic to fractional quantum Hall effects, because you get a lot of fractions, and there is no simple intuition to get like to get some terms such as just the Chen number, etc., to explain the fractional quantum Hall. So Chern Simons theory is like a very powerful tool because this can explain some underlying mechanisms behind both the integer quantum Hall and fractional quantum Hall, which I will describe later. Another experimental fact is about the chiral magnetic effect in some semimetals. By semimetals, I mean that in some there are lots of materials where in the band structure they cross each other in the momentum space. By crossing each other, I mean they will have the band structure like this. because in reality we see more like insulators, and if we tune the chemical potential carefully, we'll see that near the band edge, near the Fermi momentum, the energy can be approximated as some linear dispersed function with respect to the quasi-momentum. And because we have fermions that fills all the Fermi surface up to the left point and the right points, then naturally we'll have two branches, right? We'll have two branches near the Fermi surface. One has negative slope, the other one has positive slope, which means that near the Fermi surface, if we kind of give them a drive, then one type of electrons will go to the right, the other type will go to the left. And that's called the chiral fermions. So by chiral, I mean that near the Fermi surface, naturally we'll have like left moving fermions and right moving fermions. So if we are imposing some chemical potential balance of the left moving fermions and right moving fermions, meaning that we are tilting this free fermion band structures, like we slightly tilt down, for example, then we know that in our system, the density of the left moving fermions and the right moving fermions will not be the same. This is not a big deal in the classical in the classical physics, because in like classically we don't usually discuss the chiralities of the fermions. However, in quantum mechanics or in quantum many-body theories, this will lead to a very important fact that's called like a chiral anomaly, meaning that the imbalance of the left movers and the right movers in density will be proportional to the electric field dot producing the magnetic field that's being applied on the material. And here I showed like a very good experimental paper in 2016. So these degrees are the degrees between the electric field and magnetic field. We can see that when they're perpendicular to each other, then E dot B is 0. So there's no imbalance of the left movers and right movers. And when their angles is 0, then we get the maximum imbalance of the chiral anomaly. And it turns out that this kind of phenomenon is also topological, and we can rewrite this in a slightly revised version of Chern Simons term. And this has been very well known in the community of topological materials in the past few years.
Can you also explain this in the classical way?
In the classical way, there's no classical way.
There's no
Yeah, no classical way, because classically we don't discuss the spin of or the spin representation of fermions, right? Like classically, we'll just treat like fermions as just one single particle with some like negative charges. We don't distinguish the chirality. But in quantum mechanics, like we represent fermions as a E-rep of the Lorentz group, and therefore its left moving or right moving properties are actually related to the spin 1/2 structure. So therefore, that's called anomaly, because you don't observe this in classical setting, but you observe this in the quantum setting. Yeah. Any more questions?
So for spinless fermion, there's no parallel.
Yes. For spinless fermion, yes. There's no such effect, because this is purely due to the spin 1/2 structure. Yeah. Right. So if there are no questions, let's discuss briefly how to derive the Chern Simons term. All right, so I will use the classic example of the Hall effect, by which that we have a plane, we have a 2D plane, which we have like the 2D plane can be thought of like a 2D clean free electron gas, right? And we are applying the electric field to the positive x direction. And we are applying the magnetic field perpendicular to the plane, which is to the z direction. And then we observe some current, right? Just from the Lorentz force, we can observe some current J of H that's flowing to the y direction. And we can, just by using some simple electrodynamics, we can write the value of JH in the x component and y component. And with some simple but little bits of tensor and vector analysis, then we can write the current in the y direction, or in the x, y, 0 direction in a nice and compact form, which is Ju of H. Where here the J0 of H that corresponds to the potential term of when we're defining the vector potential, which correspond to the density. And then the x and y components, they correspond to the real current, real Hall current that we measure on the plane. And we can see that naturally this, if we write it in this form, then this naturally behaves in a anti-symmetric format, meaning that if we are applying some sort of some magnetic field with respect to the background magnetic field, then we observe some change of current, some generation of current, which is anti-symmetric to the direction of the vector potential. All right, then we can use a little bit trick from path integral. So for those of you who are not familiar with the path integral approach, so it's just identical to the Hamiltonian approach, but this way is a little bit more compact, so theorists like it. So in the path integral approach, we can write this kind of we can regard this current as the linear response of my action with respect to the change of vector potential. So this by partial s and partial delta a mu, I mean functional derivative, which is just similar to the case when we're defining the dielectric constant, that is like d, or the magnetization in the materials that we usually use this kind of linear response method to define it. And we get naively from the expression of JH the response action, which is an anti-symmetric form. Okay, you may ask, okay, we get the response. This already looks Chern Simons term, but this is not like the Chern Simons term we are referring to, because this still relies on the external magnetic field, but not the field itself. So we want to make the field dynamical, meaning that we want to see that without any like external magnetic field, if we just looking at the internal magnetic field and electric field of my system, what does it look like? And then we can perform the common trick in the path integral approach, stating that we assume that S of J mu, this is the action we want to calculate. And the way my system couples to the external gauge potential is by minimal coupling. So J dot A, which is very common in electrodynamics. And then we can get some response action. And the calculation here essentially used the identity that we can always represent the partition function of my system with either the current in my system or with the response of my system. And we can perform some Gaussian integrals by calculate the partition function directly. And from that, we can kind of calculate what Sj mu is. Here we use some tricks that we guess that my action is of Gaussian type because that's easier for theorists to do. After some technicalities and some math, we get that, okay, so for my matter field or for my real gauge field, we get similar form. So this is the so-called U1 Chern Simons term for the quantum Hall system. Yeah, there are lots of conventions in defining this, but we can kind of redefine the sigma xy as 1 over m e squared over h. So this is the usual form. 1 over m is the filling factor of the quantum Hall, and then we can represent the Chern Simons term as m over 4 pi, the integral of a wedge dA. So here wedge means that exterior product, which you can think of this as the a cross dA. So it's just a math to write this more compactly, meaning that the integral has some anti-symmetric structure that behaves more like a cross product. And from this kind of construction of Chern Simons term, you can get the flavor that the reason why we have some Chern Simons term is all because that we have some magnetic field, right? We have magnetic field, then some Lorentz force, which is anti-symmetric. That caused the current and then caused the whole Hall conductivity, etc. So anti-symmetric tensor is very crucial in constructing the whole Chern Simons term. Any questions? All right. So right now we have, here we have reached the Chern Simons term like this, but and we are left with the coefficient like a coupling constant m in the front. In this slide, we will argue that this m has to be integers, and we'll use some like advanced math, but we won't dive into much details about it. All right, so this is our Chern Simons term, right? And we know that from Stokes' theorem, the line integral over like lower dimensions can be regarded as the surface integral over a higher dimensions times like a derivative over the first component. So we can write compactly our Chern Simons term to one dimension higher form, such that we want to compute this. So how to compute this? Fortunately, mathematicians already did that for us. And there's a famous theorem that's called Atiyah-Singer index theorem that helps us compute this type of integrals of the whole space, of the whole like 4D space, 8D space, or 12D spaces for us. And the results is that we should get 2 times 2 pi squared times k, where k is an arbitrary integer. All right, And then let's discuss some some properties of the Chern Simons term, right? So we know that the partition function is defined by the integral over the whole space times e to the is, right? Meaning that if I have like a different Chern Simons term with the same system, meaning that suppose I have like s prime, I change my action a little bit, then at most it should differ with the previous one by 2 pi times k, right? Because we don't want to change the value of my partition function. And we can relate this this 2 pi k with 8 pi squared k and do some algebra. And we find that m times k prime should equal to another k. Where here k prime and k, they're integers, and therefore we infer that m has to be integers. So this is like the argument that m has to be integers. And then the next question we want to answer is that
K prime is bigger than k, and so this would be a fraction.
Yeah, those are fractions. Yes, but k prime and k, they are arbitrarily chosen. So even you get some fractions for one specific k and k prime, then you can always find some other like k prime and k so that they satisfy. Yeah, so this always holds from our argument.
But you're trying to argue that m is always.
Yeah, it's always true because this identity is always true, right?
Right.
And this k
I guess like for arbitrarily picked k prime and k, it's not. I don't see why m has to be an integer.
Are you trying to say that you can always choose an m,
yeah,
which is an integer, since you can arbitrarily pick your k and k prime over
Yes.
that space?
yeah.
That's
That
what
that
you're
is
trying to
kind.
say.
Yeah, yes. That is kind of the logic. Yeah.
Okay.
But why do you choose this particular k and k prime? So
Because we want to play around with my Chern Simons term a little bit, right? We want to change it and see what happens.
Okay.
And it turns out that if we want to change it, and suppose I change it by k, yeah, the easier way here is to kind of we can change k prime into k prime plus 1, right? We can also change k into k plus 1. And it turns out that only when m is into some integers that this general identity can hold. So yeah. All right.
Wait, sorry, repeat that again. So if I change k prime by 1 and
Yeah.
k by 1,
Yeah.
that can only be satisfied if m is an integer.
Yeah. So the thing is, we know a priori that k has to be some integers. And how to say that?
I guess you can choose a space arbitrarily of any arbitrary size.
Yeah.
You're basically that M4 or M3, you can choose of arbitrary size such that you can always construct an M, K prime and K which are integers.
Yeah.
I think that's probably the logic here.
Yeah. There's actually a little bit more math here that I neglected, but I think we can discuss the details right here after the talk. Yeah, but yeah, there's a little bit longer logical chain to derive this. Yeah. All right.
Okay. Yeah.
Then let's discuss what is the consequence of m. What's the consequence if we have m to the integers, right? So we know that in the usual quantum field theory, we can rescale the fields inside my action, such that the coupling constant should be a function of your system side, right? Your rescaling factor. However, here we see that m is always an integer. So if m changes, it has to be increase or decrease by 1 or by some other different integers. So there is like a finite gap between like two possible states of my Chern Simons term, which means that my Chern Simons term is gapped. If a system is gapped, it means that if you want to compress it, you have to like get very large energy to compress it. Meaning that if I have some quantum Hall states, then this state is incompressible. So this is also some properties of that people have long known about quantum Hall liquids. And the other application of the M is from the conductivity. Recall that our conductivity, Hall conductivity, is defined by 1 over m a squared over h. If m is to be usual integers, we identify that this can be like a fundamental component for fractional quantum Hall charges, right? Because we know fractional quantum Hall, they are composed with like 5/2, 1/3, blah, 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 meaning that the fraction should always be some integer numbers of some fractions, 1 over m's. And this is essentially the argument from Laughlin when he came up with the Laughlin wave function. So yeah, this is but here we are not using the Laughlin wave function, but just using the argument of Chern Simons term as a topological field theory, meaning that its coupling constant does not flow. Then we already can see that as like a basic component. Yeah, I'll talk a little bit more about the TQFT part because it's more involved than what I say here, because we have like a very various background. We have lots of experimentalists, so I won't dive this into details of the TQFT aspects of the Chern Simons term, but I will give an example to show you what it means by saying that it is a TQFT. All right. So in the previous slide, I showed that the Hall resistivity, or yeah, it can be regarded as like like the 1 over m state can be regarded as the fundamental component to construct any fractional quantum Hall states or integer quantum Hall states, right? Because if you have like m numbers of 1 over m states, then you get some integers. Here we are discussing a specific case, which is the integer quantum Hall effect, because it's easier. And people have came up with a lot of theory to explain that. And one commonly used one is from Priskin's model for integer quantum Hall effect. And that has the action like this. So the first term is the Judy term. So it came up to explain the linear growth of the Hall conductivity that's along the electric field. The second term is the Hall term, which is to explain the Hall plateaus in the integer quantum Hall effect.
That epsilon, is that like a Levi-Civita tensor?
Yes, the Levi-Civita tensor. Yes, yes. Here the Q is the field. The field is composed with like a 2-component fermions. I will avoid like all the technicalities, but just telling you that this Q should obey some symmetries in my system. And in my system, that is the rotational symmetry of the fermionic field, of the 2-component fermionic field within that plane, which is, so here sigma 3 is the Pauli matrix, the Pauli Z matrix right here. So yeah, as a conclusion, we have some field that characterizes the interior quantum Hall states, and this field obeys some symmetry. You can definitely apply this into some more complicated gauge theories. And this has more or less explained both the linear growth and the plateaus of the interior quantum Hall resistivity. Now let's look at the RG flow of the theory. So by RG flow, I mean that we see it in action, and we analyze the dimensions of the field, and we scale the system and see how the coupling constant, in our case that's sigma 11 and sigma 12, flow when we are rescaling our size, when we're expanding or shrinking our size. Amazingly, we see that in this RG flow, the conductivity in a 2D plane, they always flow to the integers, which is the integers on the x-axis, meaning that if we are rescaling the size, they always flow to some fixed points, and the fixed points, they correspond to the integer numbers of Hall resistances, and this means that the integer quantum Hall effect essentially is like a topological quantum field theory, and it should have some inherent fixed point that's topological, and it should only be captured by the topology of the system itself, but not anything else. So there are caveats about this flow diagram, but the basic idea is right, that yeah, when we're discussing a complicated system like this, and we saw some beautiful flows that goes to some integers, then we can guess that there should be some internal topological quantum field theories, and some topological terms such as theta terms or West-Zumino-Witten terms, etc., etc. All right, so let's then discuss something you are probably familiar with, meaning that we're discussing the Lagrangian Atonia of the Chern Simons term. So let's tentatively write down the Lagrangian like this. The first term is Chern Simons term. The second term is Maxwell term, meaning that we want to discuss both the topological one and the electromagnetism of my system, quote electromagnetism, because it may, so here the magnetic field or the electric field may not be real. It may be like artificial. You can create it like in the code atom, etc. And the usual definition of the Maxwell field tensor is just du a mu minus d mu au. And we can do the usual trick in the classical mechanics. We can compute the conjugate momentum of the field AI, and that is equal to 1 over g squared AI dot plus m over 4 pi epsilon ij aj. And we can compute the Hamiltonian of the system. And then amazingly, we get something like this. 1 over 2g squared e squared plus 1 over 2g squared b squared. Here, g is the coupling constant, like in front of the Maxwell term. And E and B, they are the usual definition for the electric and magnetic field in the electromagnetism. All right. You can ask, what if G goes to infinity? When G goes to infinity, this term vanishes, right? We only have the Chern Simons term. And we see that the Hamiltonian goes to 0. So the Chern Simons term does not contribute to the energy at all. So this is very amazing, right? And you may ask, why so? Why is there like a term that doesn't contribute to any energies but still produce some like Hall conductivities, etc.? Let me tell you why. The reason is because that Chern Simons term is heavily topology dependent, meaning that it has to be defined on some boundaries. Here, specifically, we can talk about a system with some boundaries of a torus with size L1 cross L2, meaning that we have a torus where we want to like a 2D space, and in each direction, that's periodically we have periodic boundary conditions. Say in X we have periodic boundary condition in this direction. In Y we have periodic boundary condition in this direction, and that's called a torus L1 cross L2. And we know that if a system, if like a plane wave that's living in this periodic boundary conditions, we have standing waves, right? We have standing waves, then the possible number of states are should be quantized. And this is exactly how we see the ground state degeneracy in the Chern Simons term. Because we can do the same thing as that we do for the standing waves, meaning that we can define some variables, and we see that we can rescale the system and redefine the variable x and y. We see that when x goes to x plus 1 and y goes to y plus 1, my system will remain the same. And then we can do a bit more, right? We can find the conjugate momentum and see how it changes in this periodic boundary condition. And we saw that for the conjugate momentum, if I change the position by 1, my conjugate momentum has to change by like 2 pi m, that my system will remain in the same state. So this means that we have like a series energy levels, and we're filling it with some electrons, and it turns out that the energy levels have to be m, such that after you fill all these levels, that you can change the energy states, meaning that we have some ground state degeneracy with a system to be m, and that's the similar results when we're dealing with the fractional quantum Hall effect. All right. So at last, I want to mention a little bit about the use of Chern Simons term in other systems. So this is a little bit technical, but I just want to show you like how to see or visualize the Chern Simons term for some different systems. So suppose instead of having like a uniform electric field in the quantum Hall effect, we're having some electric field that varies by both space and time. So it's a function of the quasi-momentum Q. And we can define the Hall viscosity for the second term, in the second term. And the second term, based on a lot of previous numerics, we know that it is quantized somehow. Like if we can do the RG, and we see that it always flows to some fixed point. So some theorists, they think, okay, so how can I explain that? And they thought, and the experts such as Damson, they finally decided that they use Chern Simons term. However, when you are defining this kind of specific Chern Simons term, your vector potential A and A0, they have to be carefully defined and transformed such that this Chern Simons term remains invariant. But fortunately, they have like a serious relations transformation properties that up to the second order, they can will explain the Hall viscosity in terms of Chern Simons theory. That okay, under RG it flows to some fixed point, and it's not some number depending on the coupling constant, but it's a universal number only depending on my the topology of my system. So that's the essence of the use of Hall viscosity in this context. All right, so there are a few further materials that I have not covered. For example, the non-abelian Chern Simons terms, or some Chern Simons terms with more complicated symmetries, but they are discussed in these references, especially the chapter 7 in Xiaogang Wen's book, or in the very good notes from David Tong that are listed here. Yeah, so I think that's all I want to say. Yeah, I'm open to any questions. All right, any questions? I think I went a bit fast in the.
Did you go to a few pages before?
Yeah, which one?
Yeah, right.
This one? Yeah.
What is the rationale that you can take G to infinity at a large system?
To check what?
Why can you take G to infinity?
Take G to infinity? Because G is, so here the formal reason of adding 1/2G squared is because we want to regularize the theory.
You want to eventually take it to infinity.
Yeah, we want to eventually take it to infinity. Yeah, because our goal is to analyze this one. Yeah. Yeah.
So this Chern Simons term doesn't really appear when you write down the Hamiltonian, as you showed here. So if you were to go through and do Hamiltonian's equations, I mean, would you find that the field just doesn't evolve under the Chern Simons term?
Is
I mean, then
So
yeah, okay.
it oscillates. It oscillates just like the standing waves. But from a little bit math, yeah. Let's just look at the classical field configuration, right?
Yeah.
So we can solve the Euler Lagrange equation and solve the classical field configuration. We find that Fij is 0.
Yeah.
Meaning that it should be spatially uniform.
Yeah.
But on the other hand, if you take the derivative without a component, you find that its time derivative is not 0. So if you solve it, you can find that it will oscillate around the boundary, just as what you see for the standing waves.
Okay.
Yeah, but they oscillate in a pattern that obeys the symmetry in the system, and you'll see some identical M oscillating modes, and that's essentially the so-called ground state degeneracy.
So I guess my initial question, my question was like, Hamilton's equations, you write down dHdP, the canonical momentum is
Yes.
equal to the change in the field.
Yeah.
But I guess the answer is that the canonical momentum doesn't really cover the whole story here.
Yeah, yes. So here, this is just for so you're asking this part, right?
Yeah.
Yeah. So here, this is just for the convenience, right? We can definitely we can evolve the position by 1, and we find that okay, the quantum momentum evolves by 2 pi m. We can go backwards, right? We can choose the rescaling properly such that okay, I go from the momentum space. My momentum goes add by 1, but I will find that my position will add by some factors times an integer, which is m.
Yeah.
Yeah. So it all depends on your definition, but eventually some m will show up in either x or pi.
Yeah. So
Yeah.
I mean, there's definitely an effect. It's just
Yeah.
interesting.
Yeah. That's the fascinating part when I learned it.
Yeah.
Because no one told me that when I first learned the Chern Simons theory. Yeah.
Well, thanks.
Yeah. Any more questions?
Can you
Yes.
kind of think about Hall viscosity?
Yes.
Take it from the next slide.
Yes.
I kind of understand the mathematical definition, but like what what is that? What is a Hall constant?
Oh yeah, sure. So suppose, as I said, that if your electric field is a function of a quasi-momentum, meaning that it is not spatially uniform, then you can have the Hall conductivity as a function of Q, right? And from some, you can do some math and find that you get the first term, which is 1, which is the lowest order of the small quasi-momentum, and the second term is the approximate to the Q square. The coefficient is nothing but the Hall viscosity. So yeah, this one, this eta A, this is the Hall viscosity. And it turns out that from lots of numerics and experiment, this part is a universal constant. So no matter what system you're using, they always find that this is a fixed number for either integer quantum Hall or fractional quantum Hall states. As long as you have the same filling fraction, then this term will be the same. So it's universal.
Is there any intuitive picture of understanding this?
Understanding this? Understanding this is that it's just a how to say that? Meaning that as long, so you have so your system is composed of a mu, right? A mu, you can think of the vector potential. The vector potential, usually like in some homogeneous space, like in the vacuum, then yeah, you can think of it's located around some sphere, right? Let me draw some pictures right here.
I meant the intuitive picture of like the C2 term.
C2 term. Oh no, that's.
Is there any intuition behind it at all? Like, I was trying to understand.
There's no obvious intuition, but I can explain the intuition using Chern Simons to derive this. Just a little bit more intuition. So yeah. Usually we are discussing some space. We have some vector potentials, A mu, which is A0 and A. Yeah, we can specify where it lives, right? It can live on a circle or on a sphere, etc., etc. So therefore, at each point, we can define a specific vector of A of mu. And the A of mu, when we go around the whole circle, it may or may not cover the whole circle, right? So that's what we call the winding number or the Chern number, meaning that the vector field composed with A that covers the whole boundary A dot EL or something. Around the loop, we go around the loop and find and see what changes, or whether it changes. And we know that if this is like 0, then this is trivial. But if this is not 0, for example, you get some n, some integer numbers, then you have some either Chern numbers or Chern Simons term that will explain why the winding of your vector field around your surface is not trivial, right? So right now, if you are not living on a sphere, but you kind of you're making some deformation. For example, you're making your sphere very weird. Like you can twist its shape. And this is nothing but this transformation here. You can twist the shape of your boundary. As long as it remains like well-defined. By well-defined, I mean the topological properties, the number of holes inside your base manifold, inside the space where your vector is living does not change. Then you can still have the Chern Simons term or the Chern number. And same thing for the vector. Right now you're having the vector, which is a line, right? So in defining the Hall viscosity, you can define some curvatures, right? At each point, your vector can be something like this, or it can go around itself like this. But you can still define an effective Chern Simons theory as long as the topology doesn't change. So that's the intuitive picture of using Chern Simons to explain the Hall viscosity. Any more questions? Yeah.
So what is the topological field theory and what does it deal with?
Oh yeah. So topological field theory. Let's go to the part. Yeah. So topological field theory is a quantum field theory that only depends on the metric. Yeah.
That doesn't.
But that doesn't depend on the metric. It only depends on the topology of your system. One quick example I can give is just by using RG, right? So we know that in RG, like we have some actions, right? And we have some we integrate out, we integrate over the whole space, and we have like some complicated some complicated fields, and we do dimensional analysis for the field, right? We get the field has, for example, the dimension of r cubed or something like that, right? So r is the position, and then we do the RG flow, meaning that when I do the RG, this action will either goes to 0 or goes to infinity, etc. By saying topological field theory, I mean the order, the exponent is 0. So my field has no dimension. Then that is the topological field theory. And if you're dealing with topological field theory, the usual techniques will fail. Like, for example, the techniques you use to calculate the correlation functions, like phi 0, phi r, or something like that, right? You use some techniques like Week's theorem, etc., to calculate these correlation functions, right? But in TQFT, all the techniques will fail because your theory doesn't depend on the details, but only depends on how many holes you have, right? How many holes or the topology of the system. And the basic operations are again different. So for example, you have a topological field theory on the left-hand side that has a donut. And you have another field on the right, another donut. And you want to multiply them together by 1, by 2. And by multiplying, you're kind of gluing these two fields together. You can safely neglect all the details as long as they remain the shape of two donuts. Then that's a valid operation in TQFT. Yeah, so this is like a trivial example.
So, sir, are you doing the connected sum of the two, or are you just gluing?
Gluing them, yeah, just gluing.
No, gluing. You need to define what is glue.
I'm just giving like the most trivial operation that you can think of for glue. Just multiplication of the two fields. Yeah. Okay. Any more questions?
And your Hilbert space is just.
Yeah, just some donuts, or whatever. Right. So I think that's for today. I hope you all enjoy my talk. Some of the discussions are a little bit too fast, so we can always discuss a bit later about the details. All right. Thank you everyone for coming here.